hydrogens are right there? One, yeah. We look at that carbon. He's neutral, so we know he's got 4 bonds. Okay? He's got 1, 2, 3 bonds to him. So the only bond that is missing is 1. So it must be 1 missing hydrogen. Perfect. Okay. How many hydrogens right there? 0. Perfect. Can't even get you. Let me get you. Okay, very good. You guys are rocking and rolling on skeletal structure. This arrangement, this group collection of atoms, okay, that's known as a carboxylic acid. Okay. When you have a C and an H, okay, that's known as an alcohol. Okay, so alcohol, yeah. We always think of alcohol as the one that's in beer and wine and stuff. That's ethanol. That's just one of a class of functional groups known as alcohol. And more specifically, when you have an alcohol that's attached to that kind of ring, that 6-membered ring with the alternating bonds like that, that's specifically what's yeah, that's benzene, okay? When you have an OH, an alcohol that's directly attached to a benzene ring, it's called a phenol. Okay? All right, rock and roll. We're going to treat it. This is acetic anhydride. It's a little bit less of a common functional group. Okay. And then we have phosphoric acid. Okay. And what happens is we end up converting that phenol into a new functional group. No longer an alcohol because the H is gone. Okay. This is known, easy to remember, it's a woman's name. This is an ester. Okay. All right. My little ranger. Okay, so now what I'm going to show you is touched on this very briefly in general chemistry. We like to know how this happens. Chemists want to know how this happens. We've broken some bonds and we've made some bonds, right? And so how those bonds got broken and how the new bonds got formed is what's known as the mechanism. Okay? And that's a great subject. You're going to spend a lot of time on mechanisms. I would say, you know, I tried to convince you last week, organic chemistry is not hard, there's just a lot of it. You need reps. It's just like shooting hoops or doing yoga or whatever, you need reps, okay? Mechanisms are something that students, you know, they find it a little bit harder than the average OChem idea, is mechanism. Mechanisms are just reps, just do it. When Dr. Organ teaches you a mechanism, get some scratch paper, write it over 5 times as fast as you can, keep going, okay? All right. The thing I think that makes it a little bit tricky for students in mechanisms is this, like this particular mechanism I'm about to show you, it doesn't have to be with this alcohol and this anhydride. Okay, it could be a different alcohol, different anhydride, and you'd have the same reaction mechanism. Okay? So you got to learn it. You can do your reps with exactly the one you're taught, but you need to be able to sort of generalize it. Okay, you know, same process, but with a different alcohol. All right, anyway, I digress. Okay, so we have phosphoric acid. Okay, the first step, this is called the curved arrow. Okay, one of these lone pairs on acetic anhydride base. And this is the acid. Okay? You might wonder, well, there's lone pairs all over here. Why didn't they grab one of those protons? They probably do. They probably do. But it doesn't lead anywhere. This leads someplace. Down. Eventually down a semi-one-way street. Okay, so in mechanisms, we draw a curved arrow that indicates a new bond, and then we draw a straight arrow, and we draw the result of our curved arrows. Okay. So according to our curved arrows, that lone pair up there is no longer a lone pair, it's now a bond to an H. Okay. Anytime you have an oxygen that's got 3 bonds and 1 lone pair, it's got a positive charge now. Now, this is called a carbonyl, okay? So a carbonyl is when you have a carbon and a double bond to an oxygen. Okay. When you have a carbonyl, there is a partial positive charge on that carbon. Okay? This is a polar bond. Remember these descriptions from Gen Chem? It's a polar bond. This oxygen is much more electronegative than is that carbon. Okay? Not only that, there's a resonance structure that also, altogether, everything leads to the fact that there is a partial positive charge on that carbon. Does that make sense? When you put that proton on there, the partial positive charge on there becomes even more significant. In a way, you could think of this positive charge that you put on the oxygen, that now makes the oxygen even more electronegative. Now it's really tugging on these electrons at that bond. Okay, so there's partial positive charge there. The lone pair, all lone pairs, but including this lone pair, is attracted to that partial positive charge on that carbon. We'll come down, attack that carbon. Those electrons will go up there. There's our curved arrows. I'm going to draw the result of my curved arrow. When you draw the result of your curved arrows, don't change anything other than what's indicated by your curved arrows. Okay, so there was an H on that oxygen. There's still an H on that oxygen. What I did, which may be throwing you a little bit, I took this acetic anhydride bit and I flipped it upside down. So I should have done it. That would have been fancy if I had done it in red. This is all the acetic anhydride bit. Okay? And so that carbon is this carbon. And that new bond that's indicated by this long curved arrow is this bond here. Okay? All right. What's going to happen now is you are going to get what's known as, oh, I'm sorry. I'm getting ahead of myself. Okay. Something, oh no. I wasn't getting ahead of myself. Sorry. That proton is going to come off. Okay, you can always sort of look at your final product and see, oh, well, that oxygen doesn't have a proton, so it must come off someplace. It's going to come off, something in solution, maybe probably some water or something will take it off. Okay, and then it's going to end up getting put back on this carbon. Okay, this is the one place in mechanisms where we allow shortcut. Okay, rather than showing one step where it comes off, one step where it goes on, we're just going to say proton transfer. Okay. Transferred off there and onto there. Okay? All right. So now, what happens is guy comes down here, makes a double bond. Okay? These electrons come here, make a double bond, and those electrons go up there. I'm crazy, right? This is a fairly involved mechanism for your very first mechanism you're ever looking at, yeah? Okay. Oh, I know what I was forgetting. I'm so sorry. This carbon here, okay? He's still attached. He's still attached. And our byproduct is acetic acid. Okay. This proton is still attached there. Alright. And this is again one of these situations where something's going to take that proton off. We don't know what it is, so we're just going to say B for base. There's that proton. It's there. Okay? Make sense? Any questions about any of that? It's obvious, right? It was obvious. If that was obvious to you, you have a different brain from the rest of us. Okay. Can I erase? Everybody good? Changes that we do to the procedure in the book. I wanted to let you know of those. I'm also going to show you the setup up here. Oh. Okay. Changes from book. No stir vein. They're terrible. Okay? We're not going to use that. We're going to use a stir bar or flea. You have both in your drawers. Okay? And at one point I think it talks about, oh, you may need to help the vein stir with your spatula. You won't with a stir bar or stir flea. Okay. Use water jacketed condenser. Okay. Not air condenser. I'll show you the difference in a second. This will keep the air quality in here better. Okay. Otherwise, when you use the air conditioner, it sounds like you're swimming in a vinegar bottle. That's acetic acid, and it's really strong. And we actually had one student who actually felt sick from it, so we made that change. Okay. Let me show you what the setup is going to look like. One thing I always recommend is that you guys do a what I call a dry setup. Okay? Get your glassware set up before you go get any chemical. And sometimes the book doesn't describe it that way. Sometimes, you know, it just marches into go get this chemical and stuff like that. Do a dry setup. You don't want to be fumbling with glassware that has chemicals in it. So these guys screw in there like that. Okay. These are our clamps. I don't like to use those other clamps. I got to get them to stop putting them out. They're kind of junky. Okay, so this. All right. Okay. That's the air condenser. This is the water jacketed condenser. Okay. Now, these make joints, okay? They come together, and these blue nuts are what tighten up the connection. Critical thing. Will save you from having to redo an experiment. You put the nut over that part, yeah? And then you roll this black O-ring over that. The black O-ring isn't in there. They're going to slip apart in the middle of your reaction, and you're going to be doomed. So you roll that guy over, okay? And then this guy screws on here, okay? I would have my stir bar, my stir flea in there, yeah? All right, and then open this guy up, okay? And what's cool about this, and a little bit unusual with this glassware, is that we can now, I can suspend this, this reaction flask, okay? Ordinarily, we got to grab this guy so he doesn't plump into our water bath. But because I've got that black O-ring in there, and I've got this like firmly on there, it can be suspended by the water jacketed condenser. Okay? And then I've got my hot plate. Okay. And then I need a beaker. Okay. And then that guy's going to sit down in there. Okay? We've got, you always want to make sure that this guy is centered in the center of the stir bar. You don't want it off in one corner, or if it stirs, it'll stir crazy. So you want whatever it is you're stirring in the center of the stir plate. All right? And now we need water coming into these guys. Okay, so we get these hoses here. Okay. This is another place. I'm putting tubing over glassware. I don't want to use muscle. I'm going to stab myself. And you can even put a little bit of water on there. Okay, and then this guy just slips over. Okay. Doesn't need it if it's resistant. Don't just as long as it's on there a bit. Okay, that one goes on there pretty well. And then we need one at the top. Right. Okay. You can also twist. That helps a little bit, but don't use muscle. Okay. All right. You always want to. So what's going to happen now is it's going to. Oh, I don't have the right type. Well, if I was working here, it goes, write this down. Oh, shit. All right, I'll show you guys and I'll show the camera. It goes in the bottom, out the top, and down into the drain. Okay. Ah, I'm back. In the bottom, okay, and then this connects to my sink, all right? So in the bottom spout, out the top spout, and then this top spout drains into the drain of the sink. Okay? When you turn these guys on, always be sure to use 2 hands, because if you use one hand, it goes from 0 to fire hose. And inevitably, somebody won't listen to me this year and will use one hand and will give their neighbor a shower even though they already have one today. Okay? So don't be that guy, all right? And we just need the water on, hardly on at all. And you can pick up the exit hose, which is on the top, and just as long as you're getting just a trickle out the end. We just want water flowing through the jacket. And what's neat about these water jacketed condensers is that jacket is separated from the interior of this, okay? So it will stay totally dry in here. A lot of excess water will actually wreck this reaction, okay? But the water we're running through here is totally encased in this jacket and will never be exposed to the reaction. Makes sense? All right. Suspend it like that. Stirring, etc., etc. Okay. So just some notes. You want your water bath, 50 degrees is around a setting, give or take, of 3 on your hot plate, on your heat. Don't crank this thing up, and the students get impatient and crank the heck out of it. Don't do that. Okay. You can monitor the temperature with these guys. Okay. So you can just stick this in there, all right, and monitor the temperature. You only need about 150 mils of water in here. Okay, don't fill this all the way up for a number of different reasons. You don't want water over this seam where the condenser and the conical file. You don't want water seeping in there and ruining the reaction. So you just need to heat the lower part of it. Okay, so around 100 to 150 mLs of water bath. Okay. After the 10 minutes of heating the reaction, okay, and stirring the reaction, you need it to cool. Just lift this guy up, and he can cool like that. Okay. Don't take the stir bar out with forceps. Okay. Wait till filtration. Okay. Don't worry about removing filter paper until next week. Okay? And that's part of the crystallization. So we're purifying this stuff by crystallizing, right? This is a little bit of a long pre-lab. We won't need to do pre-labs this long ordinarily because a lot of these setups and stuff like that we use repeatedly. Okay. All right. So we've got our crystals in there. All right. And so now we're ready to filter them. Okay. So we make sure that we have this ring here. We make sure that we've got our Hirsch funnel, okay, like that. Okay. Now you've got those blue pumps out here. Okay, so this fits over. 2 people can actually use these pumps at one time. We might have enough. I think we have enough where we don't have to share because we only have 8 people in class. And you turn them on by plugging them in, and then it's sucking through this. Okay. All right. So The only thing is you don't want to directly connect it to the Hirsch funnel, because you could get some stuff leaking out of here, all right? And then, you know, you get phosphoric acid into this pump, all right? So what do we do about that? Well, we're going to use what's known as a trap. Okay? So I forget what the sheet calls this thing, but we're going to use this thingy thing. Okay? Here, perfect place. Grab it on the end. Don't grab it back here and impale yourself. Okay? Twist it on. That's enough. Don't need lots and lots. Twist it on. Okay? Now this guy, it goes like there. And now this can hook up to your sidearm flask, and this side can hook up to the pump. If any water leaks out of the sidearm flask, it'll end up in this trap and won't make its way to the pump. Does that make sense? This does not need to be clamped. Okay? It's getting crowded around the clamps and everything. You can just set it on the ground. This one definitely is a good place to use a little water so that you can get that guy on. Otherwise, he's kind of hard to get on. Okay? Does that make sense? All right. Okay. And so you're going to make sure you have a piece of filter paper in here. It's white in there. Don't mistake that for paper. There's little itty bitty pieces of paper over there. You're going to put some paper on there. You're going to wet it so that it sits down nicely. Okay. And then I've got my aspirin in here. I'm going to. I can use a spatula here. I can use water to help it transfer. Okay. And then it sits and dries on there just like it describes in your book. Okay? All right. Now, at the very end, after it's dried a little bit, what we're going to do is we're going to take, these are called watch glasses. We're going to take 2 watch glasses. We're going to weigh one of them, okay? And that's going to be the bottom one. Please try to remember which is the bottom one, because these will not weigh consistent things. You're going to get an empty weight. Next week, you're going to get a full weight, okay? So, you weigh the bottom one. You scrape everything on there, including the filter paper. All right? We can separate the filter paper much easier when it's dry. All right? We put it over, okay, make a little flying saucer. One piece of tape like that, don't mummify this thing, all right? We want it to dry, yeah? So we want there to be a little bit of a gap around the edges. So one piece of tape, all right? And then we write our name and aspirin, okay? And then it goes in our drawer until next week. Next week, take it all apart. We made sure which one was the bottom one, right? Okay? And then we can get that paper out of there, weigh it, do the subtraction from the empty mass of our bottom watch glass, and we know how much aspirin we made. Okay? Does that make sense? A couple more things and then we're done, guys. All right. I guess actually one thing. Yeah. It says to don't scratch. At the very end, what hypothetically is going to happen is you're going to set it up here and boom, you get crystals. Okay? In general, we want crystallization to happen slowly. That's why you just set it up there and you wait a little bit. Probably won't get crystals. Maybe you will, maybe you won't. Okay? It says to scratch. This isn't a good situation to use that technique, and I don't really like that. It actually introduces a tiny bit of danger because those stir bars, those stir rods can crack, and again, you can slash yourself. So eventually you're going to add 3 mils of water to this, right? If you don't have any crystals that have grown, set this down into another beaker and then start to add your water, and boom, you'll get crystals. Okay? Does that make sense? Am I right, don't scratch? Okay, any questions? There's one. No, I guess we're okay. Remember, back there, when you're in the hood, there's pipettes there for your acetic anhydride. Okay. Actually, you know what? I totally forgot. I apologize. The pipetter for hexane for